A single earthquake in Southern California just broke geology, not in the future, not as a prediction. On June 28, 1992, a magnitude 7.3 earthquake struck the Mojave Desert, and 775 miles away, something impossible started happening. The ground beneath Yellowstone National Park, a place with no connection to that California fault, began to tremble with hundreds of new, small earthquakes of its own. That is not a theory. It was the measured, documented reality captured on seismometers that day. A reality that forced scientists to tear up a century of established rules. And here is the part nobody understands. This discovery, this terrifying new connection, became the foundation for a myth. An apocalyptic story of a geological fuse stretching from the San Andreas Fault to the magma chamber of the Yellowstone supervolcano, just waiting for the big one to light it. People believe California can kill us all by waking the giant. They believe the chain reaction is one of doom. And they are completely, dangerously wrong about what the scientists who found it are actually tracking. The truth is stranger, more complex, and it rewrites not just our understanding of disaster, but the very definition of a living planet. To understand the connection, you have to see the highway it travels on. It is not a fault line. It is not a crack. It is a vast, invisible scar across the American West called the Basin and Range Province. It is a place where the entire continent is being pulled apart. Slowly, inexorably, for millions of years, the crust of North America has been stretching here, thinning out like warm taffy, sagging between mountain ranges. It is an area of profound geological weakness, a wound that covers nearly all of Nevada and slices into Utah, Idaho, and eastern California. And at either end of this strained, weakened crust sit two of the most powerful volcanic systems on Earth. In the east, the Yellowstone Caldera, a monster, the active footprint of a continental hotspot that has torn a path across Idaho for millions of years, leaving three colossal scars on the landscape. The first eruption, 2.1 million years ago, another at 1.3 million, and the most recent, the one that formed the park we know today, 631,000 years ago, an engine of planetary scale change. In the west, on the other side of the Basin and Range, sits its sibling, California's Long Valley Caldera, a 20 by 11 mile depression in the Earth, located just east of the Sierra Nevada mountains, 760,000 years ago. This volcano exploded in an eruption so vast it ejected approximately 600 to 650 cubic kilometers of magma, an almost unthinkable volume that buried a huge swath of the West in a layer of ash known as the Bishop Tuff. For decades, scientists saw them as two separate entities, two sleeping giants in their own territories. They knew the Basin and Range was stretching. They knew a complex fault system called the Walker Lane was helping to rip and tear the crust along the California-Nevada border. But the idea that a tremor in California could genuinely touch the heart of Yellowstone, that was in the realm of science fiction. The laws of seismology were clear. An earthquake's energy, its ability to trigger other quakes, was a local affair. It could trigger an aftershock on a nearby fault, maybe 1 or 2 fault lengths away. But 800 miles? Across an entire tectonic province? Impossible, until it happened. June 28, 1992, just after 4:57 am local time. The earth near Landers, California, rips open. A magnitude 7.3 quake. It is violent. It is powerful. The rupture tears across the surface for over 50 miles. In the hours that follow, seismologists do what they always do. They watch the aftershocks. They map the damage. They analyze the data pouring in from their sensors. Then the calls start coming in. First, from Utah, then from Idaho, and most alarmingly, from Wyoming. The seismographs at the Yellowstone Volcano Observatory are going wild. Not just registering the waves from the main California quake passing through. That was expected. They were registering something completely new. Swarms of tiny, local earthquakes. Hundreds of them. Popping off in places like Yellowstone Lake and the northwest corner of the park. Quakes that were not there an hour before. The data was undeniable. An event in California had actively triggered a seismic response over 775 miles away. The old model was dead. The rulebook was gone. Scientists called it dynamic triggering. It's a term that sounds technical. It is not. It's a precise description for a genuinely revolutionary concept. Before landers, the thinking was that stress was transferred through the rock itself, like a crack spreading in a pane of glass. Static, physical, local, landers revealed something far stranger. The trigger wasn't the rock breaking, it was the vibration. The low-frequency surface waves from the massive quake, the deep rolling energy that travels for thousands of miles, were ringing the entire planet like a bell. As these long, slow waves rippled through Yellowstone, they were squeezing and releasing the ground. And in a place like Yellowstone, the ground is not solid. It is a fragile, fractured, superheated mess of pipes and cracks and chambers, all filled with water, steam, and gas under immense pressure. Dynamic triggering wasn't breaking new rock. It was shaking a plumbing system that was already primed to burst. It was like a ghostly hand reaching across the continent, momentarily changing the pressure in those underground pipes and causing them to pop and creak. It was a message, sent from one volatile region to another. A discovery so profound it would change how every volcano and fault line on the planet was monitored from that moment on. The Earth was not a collection of isolated systems. It was a single, interconnected machine. And here is the part that should stop you cold. 10 years later, scientists got to see it happen again, on a scale that dwarfed what they saw in 1992. November 3rd, 2002, deep in the Alaskan interior, a magnitude 7.9 earthquake tears along the Denali Fault. It is an absolute monster of a quake, one of the most powerful ever recorded on North American soil. Nearly 2,000 miles away, in Wyoming, the message arrives. Again, the team at the University of Utah seismograph stations and the Yellowstone Volcano Observatory watch their instruments light up. But this time, it is even more dramatic. Over 1,000 small earthquakes are triggered inside the Yellowstone caldera. The intensity is shocking. But it gets weirder. The quake didn't just rattle the ground. It changed the water. Yellowstone is home to the most concentrated collection of geysers on Earth. They are the surface expression of that fragile, superheated plumbing system. Each geyser operates on its own delicate schedule, a balance of heat, water, and pressure. When the waves from the Denali quake rolled through, they permanently altered that balance. Geysers that erupted regularly suddenly became erratic. Some erupted more frequently, some less. Some changed their duration. Dr. Robert B. Smith, a geophysicist at the University of Utah who had pioneered much of the early Yellowstone research, put it bluntly, "We did not expect to see these prolonged changes in the hydrothermal system. The park's entire network of hot springs and geysers, its most famous feature, was acting like a continent-sized seismic antenna. It was so sensitive that a tremor from 2,000 miles away could retune it. This confirmed the lander's discovery in the most spectacular way possible. Dynamic triggering was real. Its effects were measurable. A large enough earthquake, anywhere in the world, could reach out and touch Yellowstone's delicate inner workings. This is the real chain reaction. Not fire and magma, but pressure and water. A vibration sent down the invisible highway of the basin and range, a telegraph signal tapped out across a continent, received and registered in the bubbling hot springs of Wyoming. The internet mythmakers see this connection and imagine a string of dynamite. The scientists see it and realize they're looking at the planet's nervous system, and they were about to get a tool that let them see it in a way they never thought possible. While all eyes were on Yellowstone, the other giant was stirring. Long Valley Caldera in California. For decades, it had been a source of anxiety for geologists. Starting in the late 1970s, the ground in the middle of the caldera began to rise. Not by much, just inches, but consistently. This uplift was accompanied by swarms of small earthquakes. To the public, and even to some scientists, the signs were ominous. Uplift and earthquakes are classic indicators that a magma chamber is swelling, filling with fresh molten rock, preparing for a potential eruption. Long Valley became one of the most intensely monitored volcanoes in the world. The fear was that California's own supervolcano was waking up. Then, on October 18, 2023, a team of scientists from Caltech, led by geophysicist Dr. Zhongwen Zhan, published a study that changed everything. They had found a way to perform surgery on the supervolcano, to see inside it, and they did it without drilling a single hole. They used the internet. What they did was nothing short of revolutionary. They took 100 kilometers of existing, buried fiber optic telecommunications cable, the same kind of cable that brings internet to homes and businesses around Mammoth Lakes, the town built right on the edge of the Caldera. They plugged a laser device into one end of the cable. This technology, called Distributed Acoustic Sensing, or DOS, turns the entire cable into a network of seismic sensors. Tiny, microscopic imperfections in the glass fiber reflect the laser light back. When the ground vibrates, even infinitesimally, it stretches or compresses the cable, changing the timing of those reflections. Each fiber optic cable becomes the equivalent of 10,000 individual seismometers. For the first time, scientists had a way to create a high-resolution 3D picture of the Earth's crust, 10 kilometers deep beneath an active supervolcano. Here is what they found. The magma chamber isn't swelling, it's dying. The images they produced showed something astonishing. The top of the vast magma reservoir beneath Long Valley is covered by a solidified lid of crystallized rock. The volcano's engine is not ramping up. It is cooling down. As the molten rock cools and turns to stone, it releases trapped gases and superheated fluids, a process geologists call second boiling. It is this escaping gas and liquid, not new magma, that is causing the ground to lift. It is this process that is triggering the small earthquake swarms. All the terrifying symptoms that everyone thought pointed to an impending catastrophe were actually signs of the volcano's slow, quiet death. It's like a bottle of soda going flat. The fizzing and bubbling isn't a sign of it getting more explosive. It's the sign of it losing its energy. Dr. Zhan was clear in his assessment. "We don't think the region is gearing up for another supervolcanic eruption," he stated. But he added a crucial clarification. The cooling process may release enough gas and liquid to cause earthquakes and small eruptions. The danger is not a civilization ending supereruption. The danger is much smaller, more localized hydrothermal explosions or minor lava flows. The patient wasn't about to have a massive heart attack. It just had a case of geological indigestion. The billion-dollar fear machine was pointed at a volcano that was peacefully going to sleep. This discovery was a profound reversal of fortune. It was the scientific method at its best, replacing fear and speculation with hard, tangible data. The chain reaction myth depends on the idea that these volcanoes are hair trigger bombs. The new science shows they are more like cooling, solidifying blocks of granite. This brings us to today. July 13th, 2026, the myth persists. Every time a significant earthquake rattles California, the internet lights up with panicked chatter about Yellowstone. It happened on July 4th and 5th of 2019, when the Ridgecrest earthquakes struck Southern California. The online speculation became so intense that the United States Geological Survey had to issue a direct public statement. Dr. Michael Poland, the scientist in charge of the Yellowstone Volcano Observatory, is the man on the front lines of this information war. He is the primary scientific voice tasked with separating fact from fiction. His response to the Ridgecrest fueled panic was a masterclass in clear, direct communication. He wrote an article for the USG's website with a headline that left no room for doubt. Will the Southern California earthquakes cause Yellowstone to erupt? Spoiler alert, no. He explained the science of dynamic triggering. Yes, the shaking from California will be felt in Yellowstone. Yes, it will cause small changes in the hydrothermal systems. Yes, it will trigger microquakes. All of that is now understood and expected. But will it cause a magmatic eruption? Absolutely not. The reason is simple. The magma beneath Yellowstone is not a vast cavern of liquid lava. It's mostly solid, a highly viscous, crystalline mush, like a giant geological slushy. You cannot jiggle a slushy into exploding. It doesn't have the energy. It's too thick, too sticky, too stable. To trigger an eruption at Yellowstone, you would need an enormous injection of fresh, hot, liquid magma from deep within the Earth's mantle to reheat the chamber and mobilize it. The tiny stress changes from a distant earthquake are like throwing a pebble at a battleship. The ship might shudder, but it's not going to sink. The data from the past few years bears this out with startling clarity. The fear points one way, but the numbers point the other. Look at Long Valley. In the wake of the Caltech study showing the volcano is cooling, the actual seismic data has been almost boring. In a January 6, 2026 update, USTA's geophysicists Alicia Hodovec-Ellis and Josh Crozier described 2025 as an exceptionally quiet year for California's volcanoes. Inside the primary monitoring box for Long Valley Caldera, they recorded a grand total of just 6 earthquakes of magnitude 1. 0 or greater. 6 for an entire year. Not a sign of a brewing apocalypse. It is the sound of a volcano going to sleep. And what about Yellowstone, the beast itself? In an April 2026 livestream, Dr. Poland gave his monthly update. No signs of an impending eruption. The caldera was exhibiting its normal seasonal pattern. Minor microseismicity, as expected. And the ground was actually sinking slightly, a process called subsidence, which is the opposite of what you'd see if the magma chamber were inflating. The system remains at normal, background levels. Green, not yellow, not orange, not red. Green, the chain reaction, is real. But it is not a fuse. It is a diagnostic tool. When an earthquake happens in California, it offers scientists a chance to ping the system, to send a wave through the crust and listen to the echo that comes back from Wyoming. It allows them to assess the health of the underground plumbing. It tells them about pressure, about fluid movement, about the state of the crust. The very phenomenon that fuels the doomsday scenarios is, in reality, one of the most powerful tools scientists have for monitoring the volcanoes and ensuring public safety. The quakes are not the prelude to an explosion, they are a routine checkup. So what happens the next time the big one hits California? The ground will shake. Buildings will fall. It will be a human catastrophe on a scale that is difficult to comprehend. And hundreds of miles away in Yellowstone, seismometers will register a swarm of tiny, insignificant tremors. Geysers might hiccup. The water in the hot springs might get a little cloudy. For a moment, the park will register the distant trauma. A shiver will run through its ancient plumbing. And that will be it. The great chain reaction will have occurred, exactly as science now predicts. A conversation between two giants, spoken in a language of vibration and pressure that we are only just beginning to learn how to translate. The panic you'll see online will be based on a fundamental misunderstanding of that conversation. It will confuse the whisper of a connection with the roar of a catastrophe. It will mistake the ringing of a bell for the ticking of a bomb. The real story is not the one we fear. It's the one we are actively discovering. We built these incredible networks of sensors, these fiber optic arrays and GPS stations to watch for the end of the world. We pointed them at these monsters, expecting to find a hair trigger, a system on the brink of collapse. And instead, they are showing us a planet that is far more complex, more interconnected, and in many ways more resilient than the myths allowed. The fear was a loud, simple story about a single explosion. The truth we are uncovering is a quiet, intricate story about a conversation happening deep underground, a conversation we are finally learning to listen to. And it's telling us that the real danger isn't what the